Last time we ended up looking at the power series expansion of e to the x, and we noted that for this function f of x, the special thing about it is it's its own derivative. So if we wanted to have a power series expansion, okay, well, so what does this mean? Well, the fact that it's its own derivative means f of 0 is 1, and the derivative at 0 is 1, and every other derivative at 0 is 1. And from that, we can get that, well, this means that a0 has to be 1. This means that a1 has to be 1. Now, a2 is multiplied by x squared, so when we take its derivative twice, we get that a2, well, it needs to be a half, and a3 needed to be 1/3 of a half, which is 1/6. And in general, a sub n is 1 over n times a sub n minus 1. And so this gives us the series, the sum, k equals 0 to infinity of x to the k divided by k factorial. And again, that is e to the x. So with that, if we wanted to look at the radius of convergence, of this, and let me go back here. So the radius of convergence, well, if we use the ratio test, okay, so we take the limit as n goes to infinity of a sub n plus 1, which is 1 over n plus 1 factorial, or x to the n plus 1, over n plus 1 factorial, and divide it by x to the n over n factorial. Then this is x to the n plus 1 divided by n plus 1 factorial times n factorial over x to the n. Well, that cancels with all but one of those, and that cancel, and leave us an n plus 1 down here. And so we get the limit as n goes to infinity of x over n plus 1, and we see that that's equal to 0 for all x. Okay, so no matter how big x is, eventually n is going to get bigger, and so this goes to 0, and so this series has an infinite radius of convergence. Okay, now if we want to formalize all this for any function f of x that is continuous, together with its first n plus 1 derivatives on an interval containing c and x, we can get f of x is the sum k equals 0 to n of the kth derivative at c divided by k factorial times x minus c to r to the k plus some remainder. All right, well, what is the remainder? Well, the remainder, all right, Taylor's theorem tells us, is some value of the n plus first derivative of f divided by n plus 1 factorial times x minus c to the n plus 1, where a is some value between c and x. What we typically will do here is to bound the derivative between x and c and use that upper bound to get an upper bound on the remainder. But it will be exactly some value in there. So what Taylor's theorem gives us, or the Taylor polynomial of a given degree, degree n, is a polynomial that agrees with the function f of x at the point c up to the nth derivative. So a 0th degree polynomial would just be the constant functions with f of c as the value. The first degree Taylor polynomial, if you look at it, is just the tangent line to the function. The second degree has the same slope, value, and second derivative, so concavity at c. The third one is the same value, slope, concavity, and third derivative in c. And as we get higher and higher, we just have a polynomial that agrees with the function to more and more derivatives at that point c. Alright, so here we see a couple of examples of some Taylor series. So here, the red curve, which we don't see in the middle here, but then goes on, this is sine of x. Okay, the green is the 5th degree Taylor polynomial of sine of x, so it uses the x cubed, and x to the 5th terms. Okay, so you see it picks it up pretty well from this to this. Alright, this gold one is the 15th degree Taylor polynomial. So now we're picking up even more of the function, so it's right on it through there. And then the blue one is the 30th degree Taylor polynomial. So as you see, as we take higher and higher powers, the polynomial stays really close to the function for a longer period of time. Here we see the same thing for the tangent of the sine of x. Okay, a little more complicated function. Here's its graph. All right, now the green 5th degree Taylor polynomial matches here. The gold is maybe a little bit better, but not really a whole lot. Okay, and then the 30th, which is the green one, well, the blue one, well, only gets a little bit further. So sine works pretty well. We get good. This tangent of the sine, not so much. I mean, we never expand and get too far out. So just an example of how Taylor series sometimes can very well approximate a function, other times don't do such a good job. Well, the series version of this says that if f has a power series expansion that is valid on some radius, then the coefficients, all right, are the kth derivative at c divided by k factorial. Okay, so we're talking about finding the Taylor series of a function. Okay, centered at a particular value. This gives us we find the coefficients by taking the derivatives and plugging in the center and dividing by k factorial. Recall that a Maclaurin series is just a Taylor series centered at 0, which is what we will often use. So let's look at some examples. Alright, so we already have seen that, well, for 1 over 1 minus x, alright, that's the geometric series, so it's just the sum k equals 0 to infinity of x to the k. Alright, sine, recall that the derivative of sine is cosine. So the second derivative of sine is negative sine. The third derivative is negative cosine. And the fourth derivative is back to sine again. So that gives us this series, which we can write out as x minus x cubed over 6 plus x to the 5th over, well, 5 factorial, or 120, minus x to the 7th over 7 factorial, and so on. We get the odd terms. Okay. Cosine, alright, we get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and it keeps going, picking up the even terms. Okay. E to the x we just found. Natural log of 1 plus x we had found before, and we found it in a different way by taking the antiderivative of 1 over 1 plus x, but you can check for yourself that these coefficients would be what I get by plugging in the appropriate values. Now if we go back here, there's some homework problems on power series you can look at, and then ponder the comment following problem number 72. And we will begin chapter 2 on Monday.